So the main application of async programming is I/O-bound multitasking applications such as a web server. In this kind of application, the program needs to handle many tasks at the same time. But meanwhile, most of the time, these tasks are just waiting for I/O operations to complete, and only a very small portion of time is actually spent on doing computation. So since we are talking about multitasking here, you may wonder, why not just use threads? Well, for typical async programs, threads are too heavy. For example, consider a web server. A web server can handle tens of thousands or even more connections at the same time. If you spawn a new thread for every connection, then you will have that much threads. And thread switching will happen at a very high rate. And at this rate, the context switching cost of threads becomes too expensive, and it will lead to very poor performance. So since threads are too heavy, we need to use something else to write async program. And the solution is to write an event loop. An event loop is a special style of program. If your program is in the form of an event loop, your program will be a very big loop. And in every iteration of the loop, you will wait for some of the I/O operations to complete. And for every completed I/O operation, the event loop will run some code that handle the result of the completed I/O operation. Using event loop, we no longer have threads. There is only one single thread. So the switching cost between different tasks become very lightweight. So event loop can solve the performance issue of using threads for async programming. However, event loop also has its problem. The main problem is writing event loop directly is very tedious. Consider this scenario. Assume we have a task that needs to perform 2 asynchronous requests in sequence. After performing the first task, we cannot just wait for the second task to complete because that will block the whole event loop. Instead, we need to register the second task and wait for it to complete and run the code that handles the second task in another place and another time. So the main problem with event loop is you have to split a logically contiguous piece of code into multiple parts. Otherwise, you will block the whole event loop and result in very poor performance. So splitting code will make the code much more difficult to read and reason about. And that's the main drawback of event loops. The solution to this problem is to use callback-based API. So the idea behind callback-based API is that if the event loop is so hard to write by hand, why not provide it as a library? So we need to think, if we provide the event loop as a library, what API should this library provide? The answer is whenever the client code needs to perform some I/O operation, they not only supply the operation itself, they also supply a callback function telling the event loop what code should be run to handle the result of the I/O request. So after receiving an I/O request and a callback, the event loop simply registers the I/O operation and perform it. And when the I/O operation is finally complete, the event loop will run the registered callback, and the client code will handle the result of the I/O operation in the callback. So the main advantage of callback API over event loop is that you no longer have to split code. For example, the previously mentioned scenario, we need to perform 2 asynchronous requests in sequence. If we write code in callback style, it will look like this. So the code is grouped together. You don't need to split it into multiple parts. First, we perform the first request, request 1, with a callback. And in the callback of request 1, we get the result of request 1, X, and we perform request 2. And in the callback of request 2, now both requests has completed, and we can handle their result. So, but although callback API is much easier to write than coding event loop directly by hand, it is still not ergonomic enough. For example, you can imagine if we are not doing 2 requests, if we are doing 100 requests, then the indentation level of the code will go deeper, and deeper. You will get 100 layers of indentation at last, and that will make the code very unreadable. Besides, event loop is different. Callback style is different from direct style. So if your code needs to use control flow constructs, such as early return or loops, you need to rewrite your code in a different shape so that you can transform it using callbacks. In fact, there is a very famous word you invented to describe the pain of writing callback by hand, callback hell. And this word is mainly used to describe the experience of writing callbacks in Node.js. So ultimate goal here in async programming is that we wish we can write asynchronous code in direct style, just like synchronous blocking code. That way, the code is the most intuitive and readable. For example, the previous program that performed 2 requests in sequence, we want to write it like this. This is perfectly readable. It is much more readable than the both previous examples. But we don't want this code to be just simple synchronous blocking code. When we are performing request 1 here, we don't want the whole program to block and wait for request 1 to complete. We want this code to be asynchronous. So what capability should the programming language provide to support this style of asynchronous programming? So when we are doing request 1 here, the program must not block and wait. So it must suspend itself and save current state somewhere and register the request in the global event loop. And when the I/O operation is finally complete, the event loop needs to be able to resume the execution of this piece of suspended code from the request 1 point. So we need 2 capabilities from the language. First, we need the capability to suspend a running function and save its state. And second, we need to resume the execution of a suspended function from the saved state. That's the 2 main capabilities necessary to support asynchronous programming in direct style. So the next question is, how should we implement this? A natural idea is we already know that that piece of asynchronous code we seen earlier, it has the same semantic as the callback version. So we can rely on the compiler to transform direct style code into callback style using the famous continuation parsing style transformation. And this way we can now write asynchronous program in direct style. Another popular approach is to compile asynchronous code into a state machine. So we split a piece of asynchronous code into multiple states at suspension points. And when a program needs to suspend itself, it saves its current state and return immediately. And when we resume a suspended function, the function will start its execution from its last saved state instead of from the beginning. And this way we can also transform asynchronous program into a suspendable format. Notice that the state machine approach and the callback approach are essentially the same approach. In fact, we can turn callback style program into state machine using a series of program transformation techniques and optimizations, including lambda lifting defunctionalization and reuse analysis, but that's not I'm not going to go into the details here. So they're essentially the same approach, and what they are doing is to rely on the compiler to do the transformation and transform direct style code into a suspendable style. And this kind of approach is usually classified as stackless approach in contrast to stackful approaches as I will introduce later. So another approach is to not rely on the compiler, but instead rely on the language runtime to provide dynamic operators that perform suspension and resumption at runtime. For example, we have the stack copying approach. When a function needs to suspend itself, the runtime suspend operation will copy the whole call stack and store it into the heap. And when we need to resume this function, we simply restore the call stack from the heap, and we are done. There is a more aggressive but more efficient approach here, stack switching. When performing suspension in the stack switching approach, instead of copy the whole call stack, we just leave the call stack as is and continue execute some other code. But obviously, this needs some special runtime support because now we may have multiple call stacks coexist at runtime. So the problem with the stackful approaches are they need special runtime support. So for a multiple backend language such as MoonBit, this can be problematic. For example, in the JavaScript backend and WebAssembly backend of MoonBit, we have no multi-call stack support, so we simply cannot use the stackful approaches. The stackful approach and the stackless approach have different performance characteristics, and each have their advantage and disadvantage in terms of performance. But that's not the main topic I want to discuss here. What I'm going to discuss here is the syntax of the stackful approach and the stackless approach. At first, this topic may sound weird because in theory, the stackful approach and the stackless approach, they are just 2 implementation strategies of the same programming language feature, right? So they are implementation details, so why should they affect the design of syntax? But in practice, things are different. In typical language based on the stackable approach, such as Go, Objective-Camel with multiple support, and Lua, there is no special syntax for creating and calling a synchronous function. But in typical language taking the stackless approach, such as Python, JavaScript, C#, and Rust, program need to use explicit syntax to mark asynchronous function and calling asynchronous function. For example, the previous example will look like this in a typical stackless language. The asynchronous function itself must be marked with the keyword async. And when we are performing asynchronous request or calling other asynchronous function, we need to mark the request with the keyword await. Await indicates that the function may suspend here, and that code after the await expression should only be executed after the awaited request complete. So these two styles of syntax, the implicit one and the explicit one, each have their advantage and disadvantage. The explicit syntax is more verbose and has more syntax burden, but on the other hand, it makes the structure and semantic of the code clear. So it seems that the choice of syntax here is just a matter of taste, right? But what I want to discuss here is, why does stackful languages favor the implicit syntax while stackless languages favor the explicit syntax? Is this just a coincidence? In fact, this is not a coincidence. This is a result of a fundamental difference in the stackful and the stackless approach. Calling convention. In the stackful approach, synchronous and asynchronous functions are the same, and the compiler will generate exactly the same code for calling a synchronous function and calling an asynchronous function. But in the stackless approach, things are different. In the stackless approach, async functions have a different calling convention. When calling an async function in the stackless approach, the compiler needs to supply an extra callback parameter or build a state machine, which is different from calling a synchronous function. So if our program only ever contains static function call, this is not a big problem because it is easy for the compiler to infer which functions and which function calls are asynchronous. But when it comes to higher order functions, we've got a problem. For example, here's a simple higher order function iter. It iterates over the elements of an array and applies its parameter f to each element of the array. Now, assume we are in a stackless language and we want to use completely implicit syntax for asynchronous functions, just like Go. Now, focus on the line of code colored red. This line of code called the parameter f of iter. Now, what code should the compiler generate here? If f is a normal function, we should generate code for normal function call. However, if f is an asynchronous function, we should generate code for asynchronous function calling here, and we also need to transform the body of iter. But the problem is we cannot statically know whether f is asynchronous because the value of f is dynamic. It is a parameter of the higher order function iter. So if we use an implicit syntax in the stackless approach, the compiler will fail to compile higher order functions correctly. So in the stackless approach, it is necessary for the compiler to statically classify synchronous function and asynchronous function. So how do real-world stackless language handle this kind of high-order functions? The most popular and widely adopted approach is to simply require the programmer to write every high-order function twice, once for synchronous arguments and once for asynchronous arguments. So this can solve the usability issue. The user can decide which version of the higher-order function to call depending on whether her callback is async. However, this approach has a very serious drawback. It introduces a lot of code duplication. Literally, every higher-order function needs to be written twice with almost exactly the same function body. So this is quite bad. Can we do better here? Actually, yes. The stackless approach requires that every higher-order function must have two versions, one synchronous version and one asynchronous version. However, we can let the compiler generate these two versions of the same function for us, and this is the effect polymorphism approach. In a statically typed programming language, polymorphism allows a piece of a single function to be used with different types. And the situation is similar here. We are classifying normal functions and async functions statically. However, we can allow high-order functions to work over both normal input and async input. One way to compile polymorphic functions as adopted by Rust is monomorphism, which specializes a new version of the every polymorphic function for different type arguments. And we can take a similar approach here. We can let the compiler specialize two versions of every higher order function. For example, the iter example, if written using effect polymorphism, will look like this. The iter function now accepts an extra type parameter a, and a ranges over async or not instead of ranging over all types. And the parameter f and the whole iter function is marked with a. So this signature reads as follows. If a is substituted to async, then both the parameter f of iter and the whole iter function itself is async. However, if a is substituted to nothing, then the whole iter function and its parameter are both normal functions. And under the hood, the compiler will specialize iter based on the type parameter a and generate two versions for us as expected. So the effect polymorphism approach can solve the code replication problem. However, it also has its own problem. The type signature becomes bloated. So in the previous example, I can write the whole signature of the iter function in one single line. But if I don't split the line in here, this signature will extend outside this page into outside the screen. So type signatures of higher order functions will become bloated. Fortunately, we can solve this problem partially by using some clever syntax sugar. Notice that in the most common cases, most higher order functions only have one type parameter ranging over async or not. So we can give a special syntax sugar to this special type parameter. So we can write the previous example as follows. The keyword async question here means async or not. And the signature, this signature is polymorphic. We can substitute all async or not with async, or substitute all async or not with nothing. So the semantic of this signature is the same as the one we previously seen, but it's shorter and more readable. So the readability and bloated type signature problem of effect polymorphism is not unsolvable. So a quick summary for this part. Our goal is to write a synchronous program in direct style. And to support this, the language must provide capability for suspending a running function and resume the execution of a suspended function. There are two different implementation strategies to achieve this goal. The stackful approaches, which rely on dynamic runtime operator, and stackless approaches, which rely on the compiler to statically transform the program. Stackful versus stackless is not merely a problem of implementation detail. In the stackless approach, async functions have a different calling convention, so higher order function becomes problematic. Fortunately, we have some ways to solve this problem. Now, I'm going to jump into the next topic. So what we have just discussed is the most basic part of async support. But in practice, to provide a full-scale asynchronous programming solution, we need to do a lot more. For example, we need a scheduler that schedules the execution of async tasks. And we also need a runtime that provides I/O primitives. And there's another topic that is also often missed here, cancellation. We need the capability to cancel a running async task. This is a motivating example. It's an asynchronous function f. The function f first connects to a remote TCP peer. And after finishing the connection, it spawns a task that keeps sending keep alive packets to the remote peer after a given period, so that the remote peer won't accidentally close the connection. Now, after spawning this keep alive task, f continues to do its work with the connection. So this program seems pretty harmless, but it is actually quite dangerous because we need to terminate the keep alive task before f returns. Otherwise, the keep alive task will leak and will keep sending keep alive packets to the remote peer, wasting both local and remote resource. Another scenario is error handling. If f fails for some reason when processing the connection, we also need to terminate the keep alive task. So we can see here that for real-world async program, cancellation is necessary. We need cancellation to do proper error handling and to write code in a more natural style. So the problem here is, how can we implement cancellation of async task? First, we should make an assumption here. we assume that all tasks are only cancelable at suspension point. This is a reasonable assumption because usually async programming uses cooperative multitasking, which means that unless a task cooperatively suspends itself, we cannot interrupt the execution of this task. So based on this assumption, we need to resolve two issues. First, how can we cancel a suspended task? And second, and more importantly, when a task is canceled, how can this canceled task release the resources it held or even perform some custom cleanup logic in React to the cancellation? The most popular approach to implement cancellation is to use cancellation token. A cancellation token is a special async task or channel that represents a potential cancellation signal that may arrive in the future. We can listen on the cancellation token to wait for a cancellation signal. And to make your code cancellation safe or cancelable, the code needs to accept an extra cancellation token parameter. For example, here's a function f. The job of f is to wait for an asynchronous operation my task to complete and do something with the result of my task. Now to make f cancelable, first f needs to accept a cancellation token as parameter. And second, when waiting for my task, f should not just wait for my task. F should also wait for the cancellation token. If my task finishes first, then we proceed doing f's work with the result as normal. However, if the cancellation token arrives before my task finishes, it means that f is cancelled. So in this case, we need to release the resource held by f, perform some cleanup, and return immediately. The benefit of the cancellation token approach is that it needs no special language support. Cancellation token can be implemented as a normal library. But the disadvantage of cancellation token is that cancellation handling is manual using cancellation token. Even if the runtime makes sure all I/O primitives are cancellation safe, the programmer still need to manually accept the cancellation token parameter and pass it at everywhere. We all know that programmers are lazy. So it is very easy for programmers to forget adding the cancellation token parameter or forget passing the cancellation token somewhere. And this will result in the code being not cancel safe. And in places like error handling, we will try to cancel a task and expect that the task will be properly canceled. However, if the task is actually not cancelable, it will become problematic because the cancellation would have no effect and it breaks the assumption of your code and result in very hard to find bugs. So there is another way to implement cancellation that can solve this problem. The idea is that we can represent cancellation as an error at suspension point. So when the event loop or the user program want to cancel a suspended task, it just resumes the execution of the task. But instead of resuming the suspended task with a normal value, we resume the task with an error. From the point of view of the cancelled task, it will see an error being thrown at the suspension point. So the consequence is that every suspension point in the program now may throw an error. Even if the asynchronous operation itself never failed, we may still receive an error due to cancellation. But another consequence is that every suspension point is now automatically cancellation safe. This is a big advantage over the cancellation token approach. We don't need to do anything to make your program cancelable. So what about release of resource and handling of cancellation? Actually, even better, we can just reuse the language's error handling mechanism to perform release of resource. For synchronous program, we already need to handle release of resource in place of error. Now, cancellation is just a normal error thrown at suspension point. So using normal try catch and defer or other similar mechanism, we can handle all release of resource. And in case you need to perform some custom cleanup logic in React to cancellation, the client code only needs to write only need to catch the error with a handler and perform cleanup in the handler of the cancellation error. So in my point of view, the throw error on suspension point approach is better than the cancellation token approach in terms of doing cancellation. And as I mentioned earlier, cancellation token, although often ignored, is a very important part in async programming. So one disadvantage of this approach is that it requires language support. The language need to provide capability for resuming a suspended task with error. And second, if your language uses checked exception or explicit error handling, such as the result type of Rust and Haskell, then the type will get polluted by the cancellation error everywhere. So that can also be a small problem, but not unsolvable. So that's all for my sharing part today, but as I mentioned in the beginning, we are working on adding async support to MoonBit. Actually, we already have a workable compiler in some internal development branch, and I will show a live demo to you here. Yes, this is not, you cannot get this in the public release of MoonBit. This is an internal development branch, but this is not a static page. Yes, this is not a static page. You can see that the code is runnable. Let me try to rerun the code. Yes, you can see that the code is actually really running on the right-hand side. So in the experimental async support for MoonBit, we have two primitives here, async.suspend and async.run. Async.suspend will suspend the current async task, and the rest of the task will be passed to a callback function. If you are familiar with delimited continuation, this is the shift operator in delimited continuation. We also have an async.run primitive, which spawns a new async task, and in delimited continuation terminology, it is the reset operator. Now, this code is run in the JavaScript backend of MoonBit, so I'm using the JavaScript set timeout function to do some reusing the JavaScript event loop here. So I'm defining a async function sleep here that asynchronously sleep for duration and execute code after it. So the effect is as follows. In the main function, I spawn two async tasks, and in each task, the task will sleep for some period and print a message. These two different tasks, they tick at a different rate, and you can see from the output on the right side, they indeed output their messages in the correct order. I have also mentioned cancellation. Actually, the current implementation supports cancellation. Yeah, it's just the program is running on the right-hand side. This is also a live demo. Since we have only compiler support for now and have no standard async library, this code snippet need to write a minimalist, simple async library for performing some things. So let's just jump to the main function. In the main function, this function creates an async context, and in the context, it spawns two tasks. The first task is a progress bar. For every 210 milliseconds, it prints the current progress, and it will loop forever. So if you don't stop this task, it will run forever. But you can see from the right-hand side that the task is no longer running after the work is done. The second task is the actual worker. Since this is just a demonstrating example, I'm not doing any actual work here. The work is represented as a time-consuming sleep. And it will also increment the current progress after some time. And finally, when all work is done, this second task will raise a cancellation error. And the context will propagate the cancellation error. It will terminate all other tasks in the same context. So you can see that the done message is printed, so it means that the cancellation error is catched here. And no more progress is printed, so it means that the first progress bar task is cancelled as expected. The approach of cancellation here is the throw error on suspension point approach. Yes. Notice that the syntax and semantic of this demo is still quite experimental, and it may change significantly in the future. It is just some very early stage experiment. I just want to show that, yes, we are doing this and we are making some delightful progress, and that's all of my talk today. Thanks.